So good morning, everyone. I apologize for being late. So let me talk about MAAT at GTC. So this is a new integral field spectroscopy mode for OSIRIS at the GTC. So there is a white paper in the archive. You find there the reference, and the list of names in brackets are those people at the IEC who are involved in the project and show interest. So we have Garcia Rojas, David Jones, Eduardo Martín, Evencio María Villa, Jorge Sánchez Almeida, José Costa, Víctor Bejar, César Esteban, Nicolás Lodier, Pablo Rodríguez Gil, and Miguel Torres. So why MAAT on the GTC? So MAAT, it's an IFU, so it will provide to the GTC community with high competitive, unique capabilities. It will be complementary to the existing and upcoming instrumentation. So there are 5 points that we consider critical that will make all this possible. First, we will provide scene-limited and wide-band integral field spectroscopy at low and moderate spectral resolution. All photons will be collected because it's an IFU, and therefore we will get large efficiency. MAAT can perform absolute spectrophotometry and also spectroastrometry. And a big advantage of MAAT is that it can work under any scene conditions by means that it keeps its nominal spectral resolution regardless of the scene. Contrary to the slit, that if you open it because bad scene, the spectral resolution will be worse, much worse. We have no overheads in the target acquisition. We can do an image that can be generated from the 3D data cube. Typically, with the long slit mode in OSIRIS, you spend between 5, even 20 minutes if the targets are very, very faint. Here, thanks to the RMS telescope pointing of 1 arc-second, even better RMS can be obtained, 0.3 arc-seconds. So we will basically go straight and do the observations. So if anyone has questions, can stop. So the MAAT proposal was developed through a fruitful collaboration of a group of scientists and engineers in Spain, Australia, Denmark, and Sweden. So only in August 7th, the GTC Steering and User Committee recommended MAAT as a visitor instrument. So we are ready to start the preliminary design phase on November 1st. And the first light is planned by early 2023. In the table below, you can see a comparison of MAAT with other existing IFUs or on big telescopes. So the first one is a very popular MUSE spectrograph, which has a much bigger field of view, 1 arc-minute by 1 arc-minute as compared to MAAT, but as you can see, it's blind in the blue. So it cannot see any light below 4,800 angstroms. So the Keck has also a slicer, but only is blue sensitive. It has a similar field of view than MAAT. And Gemini has an IFU made of fibers, which is much less efficient with a tiny field of view. So MAAT will be very much unique in the Northern Hemisphere, also in the whole planet, since we have this blue sensitivity. The resolution will be from 600 to 4,100, depending on the OSIRIS choices. And the field of view is 10 arc-seconds by 14 arc-seconds, with a special sampling of 0.3 arc-seconds by 0.127. It's a mirror slicer, so it's all reflective optics. So this is an image of the famous lens quasar from SDSS. you can see the HST image with all the lensing structure of the lens quasar. And in the white rectangle, it corresponds to the MAAT field of view. So every single spaxel in this field of view will have a spectra. So below you can see the footprint of the slicer, and this is a slicer has 33 slices, each of 0.303 seconds, and you can configure the slicer in this shape, rectangular shape or square. In this case, we chose rectangular of 10 arc seconds by 14 arc seconds. In the top left, you can see some vignetting due to the OSIRIS collimator. So the basic parameters are given here. So we have, in summary, OSIRIS as a spectrograph. MAAT is a model, basically, that will go into the cartridge of OSIRIS where the masks are inserted. The field of view, we already said, is small, but still competitive. The aspect ratio is 1.4, the slicer width 0.3, and the wavelength range is from 3,600 to 1,000 nanometer. The spectral resolution is from 600 to 4,000, and the detector will be 4K by 4K. So this is the layout of OSIRIS. So we have done optical study by Robert Contant at AAO. Also, the envelope, the mechanical envelope, has been done by GTC. And also, we also did, together with Light Systems in Marseille, a manufacturing study. And in the IAA in Granada, we are working on the software pipeline. So this is the table that provides you for each of the OSIRIS grisms and VPH, the wavelength coverage and the resolution. So it's very important to note that MAAT will enhance the resolving power of OSIRIS by a factor of 1.6 times with respect to the 0.6 arc second slit. And that means that for a given grism, the resolution resolving power will be 60% higher. So that means that, for example, if you go to the VPH, instead of resolution 2,500, we will get resolution 4,000. And the same applies to low resolution. So instead of 360, we will almost get 600 resolution. So MAAT will benefit from the new OSIRIS detector upgrade that is going to replace the current Marconi. So this is the quantum efficiency, Marconi in the blue, in the red, the new E2V. With this blue enhancement, so you can really see a huge increase in the efficiency in the blue. So this is the expected efficiency of MAAT plus OSIRIS for two particular grisms. They are 1000B in blue and they are 1000R in red. So the solid thick line corresponds to the eye field. And then we have also estimates for the current long-slit mode, which is the dotted line. It's well below in the blue and also in the red compared to MAAT because the CCD, because it's using the current CCD. When we will have the new E2V on OSIRIS at the Cassegrain, the long-slit mode will be a bit higher, 5% or so higher than MAAT, but this can be clearly compensated by the fact that in the eye field you will get all the light, right? So it's not like a slit where a fraction of the light can be lost. And as an example, in slide number 9, you can see in the top right panel that for the flux inside the slit, is 80% when you have a scene of 0.8 arc seconds, the typical scene, and a slit of 0.6. So that means that you are losing 20% of the light. So that light clearly is not lost with the eye view. So it means that in some circumstances, MAAT could be even more efficient than long-slit. And in the average cases, we assume that could be similar, but still offering the big advantages of absolute spectrophotometry and many other interesting features, especially the 3D spectroscopy. So this is an estimate of the AB magnitude in 1 hour for signal to noise of 5 for these two grisms with MAAT in the new platform, in the Cassegrain platform. So you can see that in the blue at 4,000 angstroms, one can really go very deep, 23.75 magnitudes. And then in the red, it's pretty much as now beyond 6,000 angstroms. In the bottom square, we highlight the estimates of surface brightness emission. And in this case, has been a scale from the Muse exposure time calculator. Just I leave it to you. I will pass you the slides. You can also have these on YouTube. Okay, so what's MAAT? How it looks like? It's a box. It's a box. You can see in the right panel the cartridge of OSIRIS. This is basically a jukebox where the slit masks are inserted. And MAAT, to all effects, is basically occupying the space equivalent to 6 of those frames, mask frames. So in practice, one could insert and remove MAAT anytime. That's possible, but it's also interesting that always will remain inserted because one wants to respond to alerts, and also very likely MAAT will be used regularly in the instrument. So I think there's no need to remove it, but in principle can be removed. This is GTC staff changing one of the masks in the left picture, and this is very similar operation. It actually is the same operation as for MAAT. So this is the envelope, technical specifications. So that's the cartridge in the top panel. So you see the cartridge with the masks. So MAAT will be inserted there, and there is a motor with an arm that will take the module and insert it on the focal plane of MAAT. The size dimensions of the module are given here. So you can see the space envelope is 40 centimeters by 44 centimeters. And in the Z dimensions is about 100 millimeter. The weight, we will tell now. We have been doing testing last week with the dummy, and the weight limit could be increased. There's no problem with the motor. We have tested that, and we need more tests to confirm the final upper limit for the weight. But 10 kilograms sounds perfectly feasible, and maybe even more. So this is the model, the box, how it looks like from outside. So the light is coming from the telescope. There is a hole with a peak of mirror that basically reflects the light 45 degrees to the eye view, to the four optics, to the mirrors, and then the light forms a pseudo-slit that will go into OSIRIS. So in principle, there are no moving parts, neither cables, electronics inside the box. To all effects, it's just another OSIRIS mask that it can be removed from the cartridge if needed. So this is the results. Actually, this is movies. I will show you next slide that I got last night from GTC staff. And this is the results after we were testing the dummy. This is work done by GTC staff on last week on Wednesday, Thursday, and Friday, where we built a dummy, which is the picture in the left, with the interfaces that was inserted in the cartridge. And then we did all the testing, the GTC staff did all the testing to make sure that all the dimensions were correct, and also we did testing of weight limit as well. So in the it's important to mention the contribution for the construction of the dummy is done by Eduardo Martin at GTC. So we are very grateful for that. In the right picture, you see the dummy already inserted in the OSIRIS focal plane. So in the left panel here, you see this is the videos. Let's see if I can start. Oh, sorry. I think I can start for some reason only this video. So this is a video where you see, in the left, you see the MAAT dummy inserted in the cartridge. The middle is the model is moving to be inserted in the focal plane. You can see now has reached the final position, okay? And now it's inserted in the position for observations. And all the operation went very well. The motor didn't suffer any stress. And we are now learning a lot of questions that we need to iterate again in the next dummy. So this is now a movie with the dummy being back to its nominal position in the cartridge, where all the other masks are. So this operation also went smoothly and had no problem. We found a problem when we put too much weight, and which had to do with those wheels at the bottom that we might have to think how to make more smooth. It will depend also on the final weight limit that GTC will establish. But this testing campaign has been very, very successful, and now we have all the dimensions and the envelope design ready for our kickoff. So we are very grateful to the GTC staff. Oh, that's the movie. The left panel is the movie where the cartridge is setting to make MAAT align with the focal plane and be retrieved. Okay, so this is the optical concept. So this is a view. The front plot is the middle plot. The front plot is a view from OSIRIS. So what we have is a little mirror, a fold mirror, that will get the light from the telescope, and then it will be reflected to some 4 optics that we have to design to correct some aberrations, if there are aberrations with the little field of view. And then that light will go to the slicer. The slicer is represented here by the left middle stack of mirrors. You can see a picture of a real slicer as built for Keck by the same company with light. In our case, we will have 33 slicers, each of 0.8 millimeters, which corresponds to 0.3 arcseconds on the sky. So the ray tracing here corresponds to 6 slicers, okay? So you can see how the light coming from 6 slicers goes. You see the the yellow arrows. So you can guide your eyes, for example, in the top one, will reflect the light from the slicer. It will go to the first imaging mirror, and that will go to a flat slit mirror that will basically form the virtual slit. Okay, so you can see in the left panel a cross section of the drawing, where you can see the position of the slicer and the re-imaging mirrors, as well as the shape of the virtual slit, which is very curved, as you can see. And this is actually the same as the slit of OSIRIS, exactly the same topology. Okay, so let me move to the MAAT science. Basically, we believe that the reach of MAAT can offer essentially unlimited science. And then I will highlight here the focus on a selected outstanding topics that we included in the white paper. So if you go there, you can see for each of them a summary of the research and goals and why we believe this will be unique science. So this is including the nature of the low surface brightness universe, both for intergalactic and circumgalactic mediums, strong galaxy lensing studies, time domain cosmology, with strong length quasars and supernova, identification and characterization of the electromagnetic counterparts of gravitational waves, also the physical studies of the host environment of supernova, accurate measurements of binary masses, and understanding the planetary nebula abundance problem, the study of brown dwarfs and planetary mass objects, particularly very faint brown dwarfs, and also the synergies of MAAT with worldwide telescopes, and in particular, other facilities at La Palma in other wavelengths, like gamma rays, for example. So this is one of the cases, is a simulation of MAAT for the kilonova that was discovered a few years ago after the alert of a gravitational wave event of neutron-neutron merger. And this, we took the data from MUSE and we basically reconstruct the CCD frame that we will get from OSIRIS, okay? So the left top panel is the MUSE field of view of 1 by 1 per minute. So we have a smaller field of view as the right top panel shows for the 33 slicers. And then in the bottom, the big image is each of the slice spectra as seen from OSIRIS. Recall that we will go bluer than MUSE because it goes up to 3,600 nanometer angstroms instead of MUSE. And in the right panel, you can see the structured spectrum of the kilonova for 3 different epochs, the blue, the green, and the red. And as you can see, the gray area represent the spectral coverage of MUSE, and you can see how OSIRIS+MAAT will be more competitive than MUSE because it's blue sensitive, and this is particularly very important for the early moments of the kilonova event. We also will see the physics of those structures of seen around low surface brightness galaxies, in particular on starburst galaxies like ISUT W18, and MAAT will allow to discover whether these plumes, these structures, is pristine gas from the early universe in the process of being accreted by the galaxy. So also in the right panel, you see Lyman alpha emission around redshift 3 of a radio quiet quasar. And the idea will be also to observe the conditions of this gas and distinguish between inflows and outflows. In the bottom figure, you see for a particular planetary nebula observed with MUSE, you see the distribution of oxygen 2 and oxygen 3 in order to understand, to solve the planetary nebula abundance problem. So with MAAT, we can also see and understand this mystery in the planetary nebula physics. Finally, 2 more examples of cases is in the top, which is the basically spectroscopic study of brown dwarfs legacy program from Euclid. This will be challenging because those brown dwarfs are really, really faint and can push GTC to the real spectroscopic limit, because with MAAT, one can, in principle, get a better spectral resolution to have wider spectral coverage. and we will not be losing any light because the slits. And this is particularly very important when you deal with very faint objects, because you lose also significant time in the acquisition with OSIRIS, because it forces you to do images first, pointing, checking. So with MAAT, you will save all that time as well. Strong lensing. This is a strong lensing in the galaxy cluster A370 seen by HST. There are a lot of structures seen, and the identification of all these lensing features with MAAT will be very useful to build the models of critical lines and understanding better the physics of these systems. Synergy and calendar. We will be in a very exciting time. We will have MAAT starting early 2023. By that time, the LSST will be up and running. Actually, about that time precisely, we'll be delivering alerts of many, many different transient objects. HST will also continue. MAGIC telescopes and CTA will be running. Rosita and X-rays will also be working. From La Palma, we also have GO2, which is a wide field imager that will provide alerts for kilonova, for example. We can do also counterparts of JPAS, WIF, DESI, Euclid. James Webb is also very nice as synergy, because James Webb is blind below 6,000 angstroms. So that allows MAAT to do some interesting follow-up to extend in the blue the spectrum of James Webb. And very important is the counterpart, electromagnetic counterparts of the gravitational wave experiments. So this is an example of how MAAT will provide a unique opportunity to complete what is known as the time domain revolution in astronomy, because with LSST will show up objects that we don't know with the nature in many different fields of astrophysics. So having the possibility to use an eye view in a 10-meter will basically bring new discoveries for sure. So we have the kickoff meeting. This is the final slide. We can also now discuss anything you might be interested to know. So we are having the kickoff meeting on October 20, 22, and 27. And the preliminary design phase is starting on November 1st. So that's all. Thanks a lot.
Okay, if anyone has any question, please raise your hand.
Yes.
Thank you, Francisco.
Okay, it was fast.
Yes.
I tried to compensate the delay.
I have a question. Sebastian Comeron here. Can I be heard?
Yes.
Yeah.
Yes. Francisco, you have not made a comparison to Megara. What would you say that other than the contiguous wavelength range is the big difference as I see it? Do you have on other?
Yeah, absolutely. I haven't done a comparison because it's totally complementary. Let me show you. The main reasons is that there are two main unique features. One is that MAAT is a scene-limited instrument. Megara has a fixed aperture of 0.6 arcseconds per fiber. So that means that if you have a scene of 0.6 or 0.8, you cannot sample the full width maximum, right? So, but if we have a scene better than 0.6 arcseconds, with MAAT, you can benefit of the high resolution. So that's number one. And number two is the broadband spectroscopy range, because you have all the OSIRIS grisms and VPH in the list that can provide you in a single chart, for example, with resolution 1,500. You can go from 3,600 to almost 8,000, or from 500 to 1 micron. And for low resolution, with resolution 560 R300R, right? You can go from 4,800 to 1 micron. So it's offering also throughput, because in the blue, Megara is suffering of the length of the fibers, 40 meters of fiber. At least by 40% or 30% in the blue, which is not happening in MAAT, right? Because it's an imaging slicer. So we offer scene-limited broadband spectroscopy and high throughput in the blue.
Thanks.
I have another question.
Hola, Paco.
From José Miguel.
Hola.
Hola, Paco.
Hola, José.
No acabo de entender por qué dice sin limited cuando el sin medio en la palma es del orden de 0,7, 0,8 y tú tienes 0,3. ¿Qué estás desperdiciando ahí?
No. A ver, si vas al teorema de Nyquist, para muestrear el sin necesitas al menos dos.
El doble, efectivamente.
Entonces, si tienes un sin de 0,6, por ejemplo, que es un 10% de los casos en GTC, o 0,8, por ejemplo, 0,8, que es la mediana, ¿no? En 0,8 con MAAT resuelves la PSF sin problemas. Eso es lo que quiero decir con sin limited. Igual no es el término más adecuado, pero con Megara no lo resuelves, porque tienes una apertura de 0,6 segundos.
Y otro comentario, si puedo hacerlo.
Sí, claro.
Yo hubiera hecho una cosa de mucho más envergadura y me hubiera ido al foco primario.
Sí.
De GTC.
Sí.
Y hubiera puesto tu instrumento allí.
Sí.
Y entonces hubieras conseguido algo así como Muse.
Sí. Eso sería lo ideal en otro paso. Por ejemplo, si tuviéramos éxito con MAAT y la comunidad respondiera en cuanto a la demanda, que de momento ha sido muy exitosa la demanda, la intención es el de tener un IFU tipo Muse que sustituyera a OSIRIS, ¿no? Es un poco el plan. Lo de ir al primario sería muy ventajoso por el campo. Y sabes que alguna vez hemos hablado y a mí me encantaría, no solo por Muse, sino por tener multiobjeto también, ¿no? Pero el primario creo recordar que no es practicable, ¿no? Está detrás del M2 y prácticamente choca con la cúpula, casi a 1,5 metros. Pero significaría rehacer completamente la araña con donde está el secundario. Entiendo yo.
Claro,
pero
tendrías que hacer un corrector y demás.
Sí, claro, tienes que hacer un corrector. Entonces, para tener un Muse, tipo un minuto por un minuto, realmente en el Cassegrain es posible o en el NASMIT es posible. No, porque lo que haces es tener varios espectrógrafos, ¿no?
Sí.
Y ya hemos pensado en ello. De hecho, tenemos un concepto para el Cassegrain con 1 minuto por 1 minuto de arco. Pero eso tendría que ser un instrumento de uso común. Quiero decir que el presupuesto ya no tiene que ver con esto, ¿no? Porque tienes que construir un instrumento completo. El máximo campo que te permite OSIRIS es el que tenemos nosotros, ¿no?
Sí, claro.
Claro.
Hola, Paco.
Sí.
Hola, que soy Alfonso. ¿Qué tal, Paco?
Hola, Alfonso. ¿Qué tal? ¿Cómo estás? Oye, estoy en el IAC, para todos, muy importante.
Si quieres, yo estoy por mi despacho, si quieres pasar.
Sí, me pasa ahora porque parece que estoy en Granada, pero he venido y me han dicho, no se puede dar la charla en vivo. Digo, pues la daré en remoto.
Oye, unas cuestiones. Estoy de acuerdo con el comentario de José Miguel, que deberías haber ido a por algo un poco más ambicioso y que se parezca más a Muse. Pero bueno, sé que es complicado y que eso requiere dinero. Pero
Claro.
Yo te quería preguntar, que no sé si lo has dicho al principio porque me he perdido las primeras transparencias. sobre el equipo técnico que tienes. ¿Cuál es el equipo técnico que tienes y si tienes la financiación garantizada?
Sí, a ver, bueno, ha sido sorprendente. A veces no sé qué es más importante, empezar por el equipo técnico o el dinero, ¿no? Pero el equipo técnico fue lo primero, y en cuanto al diseño óptico, que es el corazón, ¿no? del instrumento, tenemos a la AO, bueno, ahora no se llama el Australian Astronomical Observatory, y en particular diseño óptico es Robert Contant, que Robert es un clásico, un óptico clásico, el que inventó el Advanced Slicer, diseñó el Mirror Slicer de Muse, también el de James Webb, y bueno, a nivel de optomecánica, pues ese es, básicamente es el AO con Robert Contant como diseñador, ¿no? Luego, por otra parte, tenemos el pipeline, que ha sido uno de los requerimientos de GTC bueno, del comité de seguimiento. Nos pedía que proporcionáramos un software de reducción de datos, ¿no? Que es fundamental para el éxito del instrumento, aunque sea un instrumento visitante, pero estoy de acuerdo, es fundamental que el software tenga unos estándares que permita a la gente explotarlo, eso es vital. Y ahí desde Granada pues tenemos bastante experiencia, también en el IAC hay mucha experiencia, que es algo que podemos hablar. Y luego hay otra parte de AIV, de toda la óptica, aunque se va a construir en Will Light, en una empresa en Marsella, no sé si, imagino que la conoces, Will Light, sí, que es la que ha construido Muse y está en Harmony también, y los espectrógrafos de DESI. Sin embargo, todavía tenemos que identificar un paquete de trabajo para la fase de AIV, controlar lo que haga Will Light. Si ellos van a alinear, vamos a ser nosotros, vamos a comprobar. En cualquier caso, hay un interés de Liverpool en trabajar en eso. También en el IAC supongo que tenéis experiencia. Luego hay una parte, hablando esta mañana con Rafa, no sabía que tenéis para coatings, ¿no? Espejos, que me ha comentado que tenéis, luego hablamos. Hay una parte vital en el proyecto que es el coating de los espejos para alcanzar máxima reflectividad, ¿no? Porque tenemos 6 reflexiones y tenemos que alcanzar reflectividades muy por encima del, bueno, por encima del 99, algo. Es posible con coatings con enriquecimiento de plata, y eso es una parte que Will Light nos la ofrece, creo que es subcontratada, no estoy claro. Pero bueno, eso es un poco una visión, luego hay detalles, y por supuesto Gran Tecan, que nos está proporcionando toda la parte de interfaces y envelope, ¿no? Luego a nivel de coste, la envolvente del coste total es 1 millón de euros, incluyendo todo, la ingeniería, manpower y construcción, una contingencia del 20% más o menos. Y sorprendentemente yo pensaba que iba a ser más complicado encontrar dinero. No tenemos todo el dinero, eso es cierto, pero han aparecido partners nórdicos, en particular en Estocolmo, en Copenhague, que bueno, pues están por la labor de contribuir financiación, que de hecho gracias a eso nos va a permitir empezar ya el 1 de noviembre, y gracias a eso podremos acelerar el proceso y acabar el diseño, tener el Final Design Review para final del año que viene. Okay. Entonces, bueno, hay muchas cosas que discutir, hay cosas abiertas, y por eso tenemos la reunión de kick-off de final de octubre. Por eso he venido aquí al IAC, para hablar con vosotros también de qué aspectos pueden resultaros interesantes también. Entonces, hay cosas abiertas, y lo que queremos es que no retrasarnos mucho en la construcción, ¿no? Eso es fundamental, para llegar a tiempo, lo antes posible, al LSST y a la nueva generación de detectores de ondas gravitacionales.
Ok, gracias, Paco.
Nada.
¿Puedo hacer una pregunta?
2 también, sí.
¿Perdón?
Y dos si quieres.
Ah, hola, Francisco, es que no sabía si me... Soy Almudena.
Sí, ¿qué
Prieto.
tal, Almudena? ¿Qué hay?
¿Qué hay? Fantástica la charla y fantástico el trabajo, enhorabuena.
Gracias.
Fenomenal. Una unidad integral es lo mejor que hay.
Bueno,
está
gracias.
bien que finalmente la comunidad evolucione en esa dirección. Quería comentarte, tú sabes que también tenemos para GTC el proyecto, ojalá sea pronto, lo antes posible, un instrumento en óptica adaptativa,
Sí.
que es FRIDA,
Sí.
y trabaja en el infrarrojo.
Sí.
Trabajar en el azul, como trabajáis vosotros, yo creo que es el mejor concepto que podéis, de todo el esfuerzo que debe haber, porque va a haber realmente un agujero en el óptico hacia el ultravioleta, porque no hay mucha instrumentación en este rango. Entonces, se van a juntar en Gran TK dos unidades integrales, una con muy alta resolución espacial y otra con sin limited, ni equisampling, pero estupendo, en la zona del ultravioleta. La complementariedad es enorme, a pesar de que no estamos en la misma resolución espacial.
Sí.
¿Por qué? Porque FRIDA va a mirar también objetos, unos objetivos, a relativamente alto redshift, donde no vamos a tener el límite de difracción, pero muy alta resolución espacial. Se va a mover todo el espectro del óptico hacia el rojo, pero vamos a tener todo el Lyman Forest, que eso es para vosotros, y esto es único.
Sí.
Esto es único, realmente no se ha hecho antes.
Pues esto tenemos que hablar, claro.
Claro. Sí, entonces, aunque no sea la misma resolución espacial, la complementariedad, especialmente porque es espectroscopía, es la forma de hacer ciencia, ¿no?
Claro,
tenemos dos unidades integrales mirando objetos alto redshift, y la complementariedad es enorme.
Sí.
Y todo el Lyman Forest está para vosotros.
Bueno, para nosotros, porque al fin y al cabo...
Bueno, quiero decir que se necesitaría, no se puede hacer... O sea, el infrarrojo es un rango fantástico, pero obviamente, como todos sabemos, necesitamos complementariedad con otros rangos.
Claro.
El ultravioleta, el óptico, la parte final hacia las bajas longitudes de onda es fundamental porque es la zona energética en la mayoría de los objetos astrofísicos.
Sí.
Bueno, ahí la pilláis, ¿no?
Bueno, eso es muy importante porque por eso comentaba la complementariedad con James Webb. Porque también ellos no van a ver la parte visible.
Claro, exactamente, ahí voy.
Entonces eso, pero lo de Frida que me decías no había caído y es cierto y deberíamos de hablar más.
Sí.
Bueno, la idea es ahora articular unos working groups que empiecen a pensar para Key Project y, muy importante, decir a la comunidad, ¿no?, que esto es un instrumento visitante que será ofrecido al CAT, es decir, que propuestas por PIs que no formen parte del consorcio, obviamente, pues se podrán pedir, igual que Hypercam o igual que cualquier otro. Entonces, yo animaría a la gente a que vaya pensando en MAAT como un instrumento que le sea útil y la complementariedad que tú dices con Frida podría hacer que haya casos únicos, obviamente.
Well, if there's no more questions, we can thank Paco for coming here and for this speech. And thank you everyone for coming and for all the patience.
I will be around the whole day today, so anyone can find me asking around. So please talk to me.
Okay. Goodbye.
Okay, thanks. Bye. Bye.